So in this video, let's go ahead and start talking about a little bit more advanced torque problems. So in the previous classworks that you were doing, every time your pivot point was always at the center of mass, or we sort of ignored the mass of the board, or whatever we were, determining the torque of. But now we're going to look at how we could use torque to solve a problem where an object does have mass. So in the previous video, I talked about center of mass. So if a board has, say, a weight of 100 newtons or a mass of 10 kilograms, we can assume that all of the weight or the force of the weight of that board is exerted at the center of mass of that board. Another way you can think about it is if you were to look at this table, let's say that the table was really heavy and the legs couldn't support it or the board wasn't strong enough. Where would it snap? So right here, you know that the board would snap right in the middle because all of the weight of the board or the force of the weight of the board is right at the center of mass. So we can assume this 100 Newton force is occurring here at the geometric center. So force of the board is 100 newtons, right? So the types of questions we might be asked are, what is the force that this leg is exerting and that this leg is exerting? But I'm going to go ahead and make it just a little bit more complicated, and we're going to actually set something on the table. So let's just go ahead and say that we set a box on the table, and let's just say the box weighs, 20 newtons, right? So my question is, this leg, what force is this leg exerting such that the table isn't crashing down, right? And what force is this leg exerting? So we'll just call those force 1 and force 2, keeping this side of the table from going down. And we know it's different just because of the location of this box, right? So I need some distances, so let me just make up some numbers here. Let's say that between here and here is 5 meters. So the entire distance from leg to leg, and this is a giant table, is 5 meters. And the 20 Newton box, we'll just say, is about 2 meters away. So this distance would be 2 meters. So that means between here and here we would have 3 meters. And the distance to the center of mass then would be 2.5 meters. So all of those numbers are going to be relevant in this problem. All right, so let's just start with one side, right? So let's start with force 1 over here. We want to know what force 1 is, or what the force this leg is exerting on this table, keeping it from falling, right? So everything that's pushing down in this direction must be equivalent to how much force this is applying, or torque this is applying, in order to hold the table up. So we need to figure out what our point of rotation is, right? And really all you're going to do is you're going to look and see, all right, if you were to push up with this leg, right, where would the table rotate about? Right? So if you did that, if you were to push up on this leg, you can sort of see that the table would rotate about the other leg. So if we're doing force 1, this right here would be our point of rotation, okay, or our axis of rotation. So we would just have to say, well, all of the force that this thing is exerting times the distance to the pivot point, which is going to be 5 meters, must be equal to everything that's pushing down in this direction. So again, we would have to go ahead and look at our forces and how far they are from this point of rotation. So we have one that's 20 newtons, that's 3 meters from the point of rotation. And then the weight of the board, which, remember, all the force of the weight of the board is happening right here in the center. So we can say this 100 newtons and multiply that by 2.5 meters. It's distance from this point, right? So let me see if I can. So basically what we're going to have is 20 times 3, which is 60, plus 250. So we get 310 is equal to F times 5 meters, right? So 310, let me just pull up my calculator here really quick. So 310 divided by 5 is 62. So the force that the first board is exerting upward to keep this table from crashing down would be 62 newtons. All right. Now let's go ahead and look at force 2. Right? So I'm going to just cover this up and we'll start again. And we're going to actually now have to change our point of rotation, right? So if we were to push up with this leg, now my table is going to rotate about the other leg, right? So my new point of rotation and I guess I'll say for force 2, right, will be there. So we know that all of the forces that are pushing down around this point of rotation must be equal to the sort of upward force or torque in that direction in order to keep it from rotating. So let's figure out what those forces are. So I have 20 newtons times 2 meters. And then again, I have the entire weight of the board, this 100 Newton weight of the board, at 2.5 meters. And that must be equal to this force, 2, times the distance from its point of rotation, which would be 5 meters. Alright, so I end up getting 40 plus 250, so I get 290 is equal to the force times 5. So again, let me pull out my calculator here quick. And I get 290 divided by 5 is 58 newtons. Now, let's just take a second and think about, does that really make sense to us, right? So the weight of this box is closer over to this leg. So it makes sense that when we include both the table and this box, that you'd be pushing down harder on this leg, hence the reason why the first force is greater than the second force, because this box is way over here to the left, is not going to be exerting quite as much force over here. Right? So that is just an example, and hopefully will help you solve some problems where we're looking at more complicated torque and involving beams with masses and things like that.